Welcome back to JVM Internals Crashcasts. I'm Sheila, and with me, as always, is Victor. Today, we're diving deeper into the fascinating world of garbage collection in the JVM. We're currently in Level 2 of our series, focusing on operational understanding of the JVM.
That's right, Sheila. We're continuing our chapter on garbage collection deep dive, and today's topic is particularly exciting: ZGC and Shenandoah collectors. These are cutting-edge garbage collectors designed to minimize pause times, which is crucial for large-scale applications.
Absolutely, Victor. Before we dive in, let's start with a quiz question for our listeners. Here's the question. What is the typical maximum pause time that ZGC aims to keep garbage collection pauses under?
Ooh, that's a great question, Sheila. It really gets to the heart of what makes these modern collectors special. Without giving away the answer, I think our listeners will be surprised by just how low this number is. It's a testament to how far garbage collection technology has come in recent years.
Indeed. Now, before we get into the details of ZGC and Shenandoah, let's quickly recap what we've covered so far. We've discussed traditional garbage collectors like serial, parallel, and CMS, as well as the more recent G1 collector. We've also talked about GC tuning and monitoring. Victor, could you give us a brief overview of why we need these new collectors?
Certainly, Sheila. As applications grow larger and demand for responsiveness increases, traditional garbage collectors often struggle to keep up. Even G1, which was a significant improvement, can still cause noticeable pauses in very large heaps. ZGC and Shenandoah were developed to address this issue, aiming to provide consistent low latency regardless of heap size.
That makes sense. So, let's start with ZGC. What are its key features?
ZGC, or the Z garbage collector, is a concurrent low-latency collector introduced in Java 11. Its primary goal is to keep GC pause times under 10 milliseconds, even for multi-terabyte heaps. It achieves this through concurrent marking, relocation, and compaction of the heap.
Wow, under 10 milliseconds? That's impressive. How does it manage to do that?
It uses a technique called colored pointers. Essentially, ZGC embeds information about the object state directly in the 64-bit reference to the object. This allows it to perform much of its work concurrently with the application threads, drastically reducing pause times.
That's fascinating. Now, how about Shenandoah? How does it compare to ZGC?
Shenandoah, introduced in Java 12, has similar goals to ZGC. It also aims for low pause times regardless of heap size. However, it uses a different approach called Brooks pointers. Instead of embedding information in the object reference, it adds an extra field to each object that points to the object's current location.
Interesting. So both aim for low pause times, but use different techniques. Could you explain a bit more about how these collectors actually work? What's this concurrent aspect we keep mentioning?
Great question. In traditional garbage collectors, the application threads need to stop completely during major parts of the collection process. This is what causes those dreaded stop-the-world pauses. ZGC and Shenandoah, on the other hand, do most of their work concurrently with the application threads.
That sounds like it would be much more complex to implement. How do they ensure that the heap stays consistent while the application is still running?
You're right, it is more complex. Both collectors use what's called a load barrier. This is a small piece of code that's executed every time an object reference is read. It ensures that the application always sees a consistent view of the heap, even while objects are being moved around.
I see. It's like they're constantly tidying up the room while we're still using it without us noticing. Now, when would a developer choose ZGC over Shenandoah, or vice versa?
That's a great analogy, Sheila. As for choosing between them, it often comes down to specific application needs and available resources. ZGC tends to have slightly lower latency, but can use more CPU, while Shenandoah might use less CPU, but have slightly higher latency. ZGC also requires a 64-bit platform, while Shenandoah can work on 32-bit systems.
Thank you, Victor. Now, let's address some common misconceptions. Some developers might think that with these low-pause collectors, they don't need to worry about memory management at all. Is that true?
That's a dangerous misconception, Sheila. While these collectors are incredibly efficient, they're not magic. Good memory management practices are still crucial. Creating unnecessary objects or holding onto references longer than needed can still impact performance, regardless of the collector used.
Excellent point. Now, as we wrap up, let's reveal the answer to our quiz question. Victor, would you like to do the honors?
Certainly. The typical maximum pause time that ZGC aims for is 10 milliseconds. This is regardless of heap size, which is truly remarkable when you consider that traditional collectors could cause pauses of several seconds on large heaps.
That's incredible. To summarize, we've learned about two cutting-edge garbage collectors, ZGC and Shenandoah. Both aim for consistently low pause times, even with large heaps, by doing most of their work concurrently with application threads. They use advanced techniques like colored pointers and load barriers to achieve this. However, good memory management practices are still important.
Absolutely, Sheila. In our next episode, we'll be moving on to JIT compilation, another fascinating aspect of JVM internals. We'll explore how the JVM translates bytecode into native machine code for improved performance.
That sounds exciting. Listeners, if you've enjoyed this deep dive into modern garbage collection, please subscribe to our podcast and leave us a rating. Your support helps us continue producing these in-depth explorations of JVM internals. Until next time, happy coding!